In this video, we will learn about how bonds can rotate and what impacts bond rotations have on the structure of a molecule. Although all of our line angle drawings are flat and static, that is not how the real world is. There's lots of kinetic energy in the world, and so molecules can always have bonds that are vibrating and also bonds that are rotating. These rotations of bonds manifest themselves as changes in the conformation of the molecule. So to give you an example in line angle drawing form, I can draw these two different drawings for the same molecule. They differ by where this methyl group seems to be. And at the end of the day, I could say that that's actually just a rotation around this bond. I've essentially rotated that bond, kind of like I'm rotating my pen here. Another way to view this is to draw in all of the groups around the bond that we're viewing as rotating. So if we're viewing that bond and viewing that as rotating like so, then you can kind of see that a 180-degree rotation around here would take the group that's in plane from pointing down to being now pointing up like so. Right? And at the same time, the group that would be wedged here would be in the back. It's hard to visualize this in line angle drawings, so we use a different type of drawing that's called a Newman projection to help us visualize these bond rotations. And so the idea is to, again, look down your bond of interest. You draw a circle to represent the front atom, and you draw in everything attached to the two atoms of the bond you're interested in. And in the front, the bonds will go to the middle of the circle, and in the back, the bonds will go to the edge of the circle because the front atom is the circle, and that's covering up the back atom. To show you what this looks like, I will take this molecule right here, ethane, and I'm going to do so from this perspective. And I need to draw my front atom, so as a circle. So that's kind of the carbon number 1 here. If I'm taking the position of this eyeball, it looks like I have a hydrogen in the plane going straight up, so that gets me to look like that. And then I should have the two hydrogens to the left and the right. And you would fill those in like so. It's not clear which is which. I will highlight a little bit for you. So this hydrogen would be this one, and that hydrogen would be that one. For carbon number 2, that's the one in the back of the Newman projection. Those bonds, again, are now going to stop at the edge of the circle. If I look at what's in the plane of my eyeball, it's this hydrogen that's kind of pointed down, so 180 degrees from that hydrogen. So in the back, that would look like so, with the other two hydrogens like this. Again, give you some color coding like this. So the hydrogen that is in red is going to be the same as the one that's in gray, and the one that shows up in blue is on the same side as the one that's in orange. And so since molecules can have many different conformations, you can imagine that a bond can rotate many different angles, and thus each of those conformations are slightly different from each other. Then we need to ask the question, well, which of those conformations is the most stable and the most relevant picture of the molecule that we should think about? Turns out that there are two main areas that we'll want to think about. So we'll think about eclipsed conformations and staggered conformations. These tend to be either kind of the highest energy or the lowest energy respectively. An eclipsed conformation looks like this. So when we say eclipse, what we're saying is that we've rotated the back atom in my drawing here such that it's kind of lined up with the front group. So I've rotated around the bond such that the groups on the back atom are now in line with the groups in the front. That looks like this from the side view, so it kind of has the two hydrogens like this in the plane. That's called an eclipse conformation, and it's higher in energy. The staggered conformation looks like this one right here, where all the 6 groups on the 2 carbon atoms are evenly spaced out. That's why it's called staggered. And if you're looking at kind of the line angle drawing, you get this zigzag drawing that's in the plane. Right? So this is one reason we prefer to draw our alkanes as zigzags, because that reflects a staggered conformation. The reason for this difference in energy is attributed to torsional strain. And torsional strain is this idea that when you have two groups eclipsed like so, that just has an increased amount of energy. We call that increased amount of energy torsional strain. To understand the origin of this torsional strain, there's a lot of different explanations that people use. We'll focus on two of these. So the first explanation you can think of as being a valence bond theory approach, which is to say that electrons repel each other, and by putting electrons like this in these two sigma bonds here relatively close to each other, they're going to repel each other. That is leading to this like increase in energy. So it's common for organic chemists to use kind of a symbolism like this to indicate those two groups are repelling each other. So the electron density is too close, that increases the energy of the system. The second and more accurate explanation is one that derives from molecular orbital theory and a different type of theory, which is called NBO theory. This stands for natural bond orbital theory. And NBO theory is something we won't get into the math of, but it's intended to bridge the gap between valence bond theory and MO theory. And so the explanation that we're seeing is, rather than thinking about the eclipse conformation being raised in energy, that was the first explanation, using NBO theory, what we can see is that the staggered conformation is lowered in energy. Right? So it's kind of two different views on the same question. Again, valence bond theory is asking us why is one higher, NBO theory is asking us why is one lower. Right? The term that we use to describe the explanation here is called hyperconjugation. So the word conjugation should make you think of resonance and delocalization. But here, because we don't have any pi bonds, this is a little bit different, and so that's why we have an idea of hyper in front here. So what's going on is that we are thinking of an interaction between a sigma bond and a sigma anti-bonding orbital. So what this looks like then is we basically have a sigma bond with a pair of electrons in it, an empty sigma star here. If those two interact at all, then we should mix them a little bit, and we make new orbitals that look like that, right? Because anytime two orbitals mix, you will create one a little bit lower in energy, one a little bit higher in energy. And then in doing so, that overall can lower the energy of these two electrons, right? So by mixing these two orbitals, we can get two electrons to be a little bit more stable. That's hyperconjugation. Again, this is a natural bond orbital view. I will first draw it out for you and then show it to you in a computer form. So the idea again is that we have this sigma bond, so you can think of it as coming from that kind of sp3 looking orbital right there. The sigma star orbital turns out to look like this. And it's essentially meant to show you that there is some amount of orbital volume that's kind of on the other side here. So the bond again is right here. That's defined by the sigma orbital. The other side of this is empty space, where we don't think of there being electron density. That's where the sigma star has some amount of potential volume. And so you get this interaction that's going from here to here. That's very nicely lined up. It almost looks like a pi bond, right? It looks like two orbitals kind of side by side mixing a little bit. I think it helps to look at this in the computational forms. So here I'm showing you a model of ethane. It's in the staggered conformation like this. And so I'm going to go ahead and turn on the CH sigma bonding, well, natural bond orbital. Looks like this right here. And so I'm showing that to you in red, blue. And so you can kind of see how that volume is really showing you where that sigma CH bond is, right? So the line that we draw on our line angle drawings for a CH bond really are actually trying to show you a volume that looks like this. That's where the electron could be found 95% of the time. So now I'll show you the sigma star of the CH bond, and that looks like this. So I'll try to always show my empty orbitals as green, yellow. And so this, I think, gives you a good idea of how things line up, right? So we have this overlap in the middle right here that you can see. So this interaction right here is what I'm trying to show you in this energy level diagram. Right? So the red-blue orbital on this side, green-yellow on the right. The evidence we have for this is that actually you can see that the carbon-hydrogen bonds are different in the eclipsed and staggered conformations. When eclipsed, the bond length is actually shorter than when it is staggered. And this is a reflection of the fact that whenever we put any electron density and mix it into an antibonding orbital, that tends to increase bond length. So the new natural bond orbital here, or the mixing of natural bond orbitals, tends to lead to an increase in bond length because we could put a little into antibonding. That leads to this longer CH bond. Now that we have this idea that there are some conformations that are more stable than others, let's look at the actual changes between them in energy level diagram form. So again, we'll look at ethane, and it turns out if you go through and kind of plot the energy of the molecule as a function of the rotational state of the bond, the carbon-carbon bond, you can get to an energy level diagram that looks something like this right here, where, as you might imagine, we should have our eclipsed being high in energy, our staggered being lower in energy, eclipsed again being higher in energy, staggered being lower in energy. This kind of difference between staggered and eclipse comes out to 3 kilocalories per mole. It's relatively small in the grand scheme of things, but still enough for us to observe a difference. I'm going to again pull up a computational animation that'll help us visualize what's going on. So here I have ethane again, but this time we'll kind of go through an animation of the rotation of the bond. And so what you're kind of seeing here is the back carbon is rotating 360 degrees, and you can kind of see how that goes from the staggered conformation into the eclipse conformation, staggered, so on and so forth. I'll also show you this from the side just to give you a sense of kind of that eclipsing interaction again. So here we have our molecule in staggered conformation, here it is eclipsed. You can kind of appreciate how these relate to our line angle drawings. So going back to that energy difference of 3 kilocalories per mole, what use is that number? Well, it's useful because we can use that number to get a little bit of information about what the equilibrium distribution of conformations is. And so if we take the understanding that we'll treat this as our free energy difference, so there's a difference of 3 kilocalories per mole between those two conformations, we can plug that into a friendly equation here to get us to an equilibrium constant for the reaction right here. Right? And so when you do this, that will then tell you kind of roughly what ratio of staggered conformation you would have to eclipsed conformation. In this case, the math tells us there is approximately 100 to 1. So if you look at 100 molecules, 99% of them should look staggered. Maybe 1% of the time you might catch it in an eclipsed conformation before it's come back down to the staggered conformation. All right, let's look at it one more example. So for a bigger molecule, butane. And for butane, we will look down the middle carbon-carbon bond right here. Turns out when you do this, things are a little bit different because now there's different groups that are attached to the two carbons of the rotating bond. So we could start off in the eclipsed methyl group version. You could take that and rotate a little bit. Now you have staggered, but the methyl groups are close to each other. You could keep going to eclipse, but now it's not two methyl groups eclipsed, but rather methyl group and a hydrogen and another methyl group and a hydrogen eclipsed. And then finally, if you keep rotating, then you can put the methyl groups kind of totally opposite of each other. And so you should intuitively expect that these conformations will have different energies because they're not all identical. We do have names for these. So what people will start to call these is kind of referring to the two groups attached to that bond and referring to their relative locations around the rotating bond. So when they are eclipsed with each other, we would call that syn, and more specifically we call it syn coplanar because they're kind of in a single plane. In many other resources you'll see the word periplanar used instead of coplanar, but they're intended to mean the same thing here. When you have a staggered conformation that is not the lowest in energy, we call that a gauche conformation. And finally, when you have the staggered conformation that puts the two largest groups opposite of each other, we call that the anti-coplanar or the anti-periplanar conformation. You can plot all of this onto an energy diagram. So again, plotting kind of rotation around the bond and the energy of the molecule. And what you would see if you do that is that, again, they're not all the same. You go from a very high energy state when the methyl groups are eclipsed to relatively lower when we're staggered, but the methyl groups are close. We go up again in energy when we eclipse again, and then we go down all the way to the lowest point when the methyl groups are the furthest apart. Give you a sense of energies here. Now, because methyl groups are bigger than hydrogens, when you have two methyls eclipsed, that's getting you up to 6 kilocalories per mole of energy over the completely lowest state. When things are eclipsed but not having the two largest group eclipsed here, so just hydrogen and methyl, that's about half as much of an energy barrier. And finally, the gauche conformation is fairly low in energy, so it's less than 1 kilocalorie per mole higher than putting the two methyl groups anti-periplanar to each other. I'll pull it up again in animation form. So that is right here. And what I'm going to do is animate it again with the back carbon rotating around, and that'll just kind of show you the methyl group's position relative to everything. So I'm going to look at this from the side now, and just to point out that you can kind of see how these methyl groups are even, they're trying to avoid each other. So even this carbon-carbon bond, so the N carbon-carbon bonds, are rotating to try to avoid putting a hydrogen there in the middle here. Right? So there's other conformational preferences on the outside that we're not even thinking about. This is the other eclipsed conformation, the not as high energy eclipsed conformation. And finally, here's the anti-coplanar conformation. And so this anti-coplanar conformation is the zigzag that we draw in our line angle drawings. So the point of this video was to get a look at how alkanes have molecular motion, how they change their shape through rotation of bonds. The energy preferences between conformations can be thought of in two different ways. The steric repulsion between two groups, so the electron density of the bonds repelling each other. And you can also think of it as stabilization of the staggered conformations. So seeing a filled orbital interaction with an empty orbital and having that overall stabilize the energy of a pair of electrons and thus stabilize the molecule in that conformation.